All righty, how's everyone doing today? Doing good, doing good. How anyone go to the Penn State Learning Review last night? How was that? Oh, they have a recording too. That's convenient. That's very convenient. Let me just open that. Yeah, so there's a I'm assuming it's where you can find it. Yeah, whatever they said. I'm not going to pretend like I know where it is. Alrighty. So exam tomorrow. So what would we like to look at? Number 13. Okay. All right. So for this one, we need to find and classify the critical points. Of the function. F of xy is 8xy minus x to the 4 minus 2y squared. Okay. So first we need to find the critical points by setting the partials equal to 0 and either seeing where the partials don't exist or where both partials are 0. So the partial of f with respect to x is 8y minus 4x cubed. Set that equal to 0. And then the partial with respect to y is going to be 8x minus 4y. Set that equal to 0. So there's nowhere where either of the partials doesn't exist. So we're either what's going to happen with these is each of these is either going to give a relationship between x and y. So we can get y as a function of x or x as a function of y. Or we're going to get a specific value or set of values for one of the variables. So for instance, if we had like x squared minus 1 equals 0 for one of them, for instance, that would tell us x has to be plus or minus 1 in that case. Sometimes we get that, which is nice, but often we just get a relationship between the two, and then we have to plug that relationship into the other equation to solve for one of the variables, and then use the relationship to figure out what the other variable is. So we could do that with either one here. The easiest one to do is look at the second one. What does that tell us about the relationship between x and y? Right, 8x is equal to 4y. So then 2x is equal to y. So we get y is equal to 2x. Doesn't tell us what x or y is at the critical point, but it tells us at the critical point y has to be equal to 2x. Oops. And so we're going to use this relationship in the other equation. So wherever we see y, we're going to replace it with 2x. And then we're just going to be left with an equation in x, and we can solve for x. So we get 8 times 2x, which is 16x, minus 4x cubed equals. So let's, let me just set this equal to 0. We can factor out 4x here. So we got 4x times 4 minus x squared. You know what, let me erase you, it's fine. And we know that's equal to 0. So then what x values satisfy this equation? Right, so x equals 0 satisfies the 4x equals 0. And x equals plus or minus 2 satisfies the 4 minus x squared equals 0. Okay, so that gives us 3 x values at the critical points. And we know the y value at each critical point is equal to 2 times the x value. So we get the points x equals 0, y equals 0, 2 times 0. We get the point x equals 2, y equals 2 times 2, which is 4. And x equals negative 2, y equals 2 times negative 2, which is negative 4. So these are our critical points. All right, so that's about half the problem. About half the problem. The other half is we need to classify those critical points. And to classify the critical points, we need to plug it into the discriminant equation. So remember, the discriminant is, and do the second derivative test. So the discriminant is fxx times fyy minus fxy squared. So fx is 8y minus 4x cubed. What is fxx?
Should it be negative 12x squared?
Correct. Yes.
Confused
So you
with
take the
that.
partial with respect to x, and then you take the partial of that with respect to x, and we get negative 12.
Like in the solution you wrote, you had put negative 8x squared, so that's why I was confused.
Okay, yeah, I knew there's probably going to be at least one problem where I made a dumb mistake. Let me look at my solutions. Okay, well, we'll go through and do it here, and I will go back and fix any that there is an issue with. Gonna be completely honest, I was about halfway through a bottle of wine at that point, so please point out any places where it looks like I made a mistake. So that we got negative 12x squared there. FYY, we get negative 4. And it doesn't look like it's going to change the answers, but that's okay. I'll go ahead and fix it. Minus fxy, which should be 8 squared. So we get 48x squared minus 64. All right. So let me rewrite that. We have 48x squared minus 64. And let's plug in each of our critical points. So we got 0, 0. So the discriminant at 0, 0 is going to be 0 minus 64, which is negative 64. And we know if our discriminant is negative, there's nothing more we need to do. We know it has to be a saddle point. So neither a local min nor a local max. Nice and easy. Then we plug in 2, 4. And we get 48 times 4 minus 64. So, so we get 96. 192 minus 64, which is clearly positive. But we get 128, right? I believe. Yeah. So we get the discriminant at 2, 4 is positive. So if it's positive, it's either a local min or a local max. And then at this point, it works like the second derivative test for functions of one variable, right? We look at f sub xx now. And if it's negative, it's concave down. So it's a local max. If it's positive, it's concave up. So it's a local min. So fxx of 2, 4. Well, we said fxx is negative 12x squared. So that is negative 48, which is negative. So we get a local max. So we did the discriminant we saw was positive. So then we check fxx. And then we see it's negative, so it's a local max. So then we do the same for negative 2, negative 4. And it works verbatim what we did just above. So we see we get 128 when we plug it in, which is positive. So then we check f sub xx at negative 2, negative 4. And then we see the same thing. We also get negative 48, which is negative. So we get a local min at negative 2, negative 4. Oh, sorry, local max, local max, local max. Okay, sorry. Was the main point of confusion the numbers for this one? Okay, sorry about that. Let me bring that one up. That was number 13. Let me make a note. Ah, yes. Okay, so it didn't change anything materially, but I can see why that would be confusing. Okay, number 17. All right. Okay. So we're finding the max and min. Of the function xy. On the ellipse, x squared plus 4y squared equals 4. Okay, so this is a Lagrange problem. We have an equation which tells us the set of points we're considering when we want to find the max and min. So these are the set of points we're looking at. This is a constraint equation. That's our g of xy. And we have a function we want to maximize and minimize, that is xy. So we set up our equations. Give myself more room here. So the partial of f with respect to x is y. And we know that's equal to lambda times the partial of g with respect to x. And the partial of g with respect to x is 2x. So it's lambda times 2x. So the partial of f with respect to y is x. We know that's lambda times the partial of g with respect to y, which is lambda times 8y. And then it also has to satisfy our constraint equation, which is x squared plus 4y squared equals 4. All right. So these are the equations here. First order business, can lambda be 0? Are there any x and y which satisfy these equations if lambda is equal to 0? So is that a possibility here? I'm glad they threw a problem in here where lambda actually is allowed to be 0. But in this case, it's not. Because if lambda is equal to 0, the equations tell us both x and y have to be 0. And you can't satisfy the constraint with the point 0, 0, right? 0 squared plus 4, 0 squared is not 4. Okay, so lambda equals 0, not possible. So let's assume lambda is not 0. And then we're going to not care about what lambda actually is, just that it's not 0. Okay, so lambda non-zero, right? So what we can do here is so we can get the same thing on the left-hand side of both of these. I believe that's what I did. So you can multiply both sides of the first equation by x and both sides of the second equation by y. So the first equation, multiply both sides by x, you get xy equals lambda times 2x squared. Second equation, you multiply both sides by y, you get xy equals lambda times 8y squared. And the reason we do this is so both left-hand sides are equal to each other, so we can set the right-hand sides equal to each other to get a relationship between x and y. Okay. Right. Okay. So we already know lambda is non-zero, so we can divide both sides by lambda. So we get 2x squared is 8y squared. We could divide both sides by 2, of course. And we get x squared is 4y squared. And so this tells us when we take the square root of both sides, that x is equal to plus or minus 2y. Does everyone see this, right? So if you replace x with 2y, right? If you square 2y, you get 4y squared. But similarly, if you square negative 2y, you also get 4y squared. So this equation tells us x can be either plus or minus 2y. Okay, so we have a relationship between x and y. Now we're going to plug this into the constraint. So when we do that, we get, plugging in either plus or minus 2y, we get 4y squared plus 4y squared is equal to 4. In other words, 8y squared is equal to 4. Y squared is equal to 1/2. Y is equal to, plus or minus square root 1/2. And so then using the relationship we know between x and y, namely that x is equal to plus or minus 2y. We get, so square root 1/2, x can either be equal to positive 2 times that. So 2 times square root 1/2. So square root 1/2 is 1 over root 2. Let me write it like that. And then 2 times 1 over root 2 is 2 over root 2, which is just root 2. And then we also get the point where x is negative 1 over root 2. So we get negative root 2, 1 over root 2. And then we do the same for negative. Y is negative 1 over root 2. So we get negative 1 over root 2. X is negative 2 over root 2, which is negative root 2. And then we also get negative 2 over root 2. So we get root 2, negative 1 over root 2. Okay, so these are our points where we need to check f. Oops. So where the two guys have the same sign, xy becomes root 2 times 1 over root 2, which is 1. And where the two guys have opposite signs, we get negative 1. And so 1 is our max, negative 1 is our min. Sorry, kind of hard to see what it's saying here. F of, so I have the plus minus. So that is just sort of shorthand for saying root 2, 1 over root 2, and then negative root 2, negative 1 over root 2. And then the other one I have negative plus and then plus minus. That means they have opposite signs. But yeah, that's where I got the 1 and then the negative 1. Hang on. Oh, forgot to stop video. Lovely. Does that clarify what's going on with that problem? Okay. What else would we like to look at?
I have a specific question from number 8 that I was hoping to answer.
Okay.
So, in the solution, hold on, I'm just getting it up. Okay, yeah. So when you were finding the unit vector in number 8, you did 1 divided by the vector 3, 0, 2. But I was just kind of curious why you used the vector 3, 0, 2. Because like when I first saw the problem, I initially thought you would use a vector from the point 1, 2, 1 to the point 3, 0, 2 instead of just making 3, 0, 2 a vector.
I did. Ooh, thank you. Yeah, I misread the problem. Thank you. I just really skimmed through that. Good point. Okay. Let me write that down too. Thank you. Thank you. Yep, be careful. Be careful. You're absolutely right. So number 8, let's fix that. So so the direction is going to be we'll say V is you know what? Let's do it this way. Okay. We'll let P be the point we're starting at. 1, 2, 1. And Q is going to be the point we're going towards. 3, 0, 2. And so the direction is going to be the vector from P to Q, which would be 2, 2, negative 1. That's a perfectly fine direction if all you care about is direction. But if you have to calculate the directional derivative, you always need to get. Sorry, what was, hang on. The exam times are the same as the last exam. It's not posted yet. Yeah, but I sent out a Canvas mail that had that info. It's the same times as last time. Yeah. 2, negative 2, 1, yes. Yep. That's our 2, negative 2, 1. Thank you. And so when you're calculating the directional derivative, we have to turn that into a unit vector. So 1 divided by magnitude of vector PQ times vector PQ. Magnitude of this guy is just square root 4 plus 4 plus 1, square root 9, which is 3. So we get 2/3, negative 2/3, 1/3. Right. And so let's see what the solutions should be. So we calculated the gradient of f at 1, 2, 1. That is 5, 2, 2. And so the directional derivative in the direction of the unit vector u of f at the point 1, 2, 1 should be the gradient of f at 1, 2, 1, oops, dot our unit vector u. And so that's 5, 2, 2 dot 2/3, negative 2/3, 1/3. And so we get 10/3 minus 1/3, which is 9/3, which is just 3. Should be 3.
Wait, sorry. Where is the 3 in the denominator coming from again?
That's the magnitude of PQ. We turned it into a unit vector. So the magnitude is square root 2 squared plus negative 2 squared plus 1, square root 4 plus 4 plus 1, square root 9 is 3. Does that?
Yeah, that makes sense.
Okay. Okay. So sorry about that one. I hope that is the last mistake. It should be 8/3. Wait, so we got 10/3 minus 4/3 plus 2/3. Yes. So not minus 1/3. Yeah. Eight-thirds. Yep. You're right. Okay. Number 15. All right. Okay. So number 15, we need to find the absolute max and min of a function on a closed bounded region in R2. So find the max and min of RG, which is x squared plus y squared plus 2x minus 2y. on the upper half, so on the top half, of the disk, x squared plus y squared less than or equal to 4. And it's the upper half, so y is going to be greater than or equal to 0. Okay, so looking at this, we know it's not just a Lagrange problem, because we know the set of points we're considering is given by an inequality. Right here. So an inequality means you're just going to be considering a closed bounded region, and you have to do like the critical points inside the region step, and then consider what's happening on the boundary, and possibly use Lagrange on the boundary. But as we'll see, may or may not be worth using Lagrange on the boundary. So let me reiterate that. If you see an inequality somewhere in your max and min problem for the set of points you're considering, that tells you it's the two-step guy. You need to find the critical points, and then you need to find max and min on the boundary. And the max and min on the boundary could be Lagrange, or it could be the other method we're talking about, and we'll actually do that method here. But it's a dead giveaway if you see an inequality somewhere in there. Okay, so let's sketch our region. So x squared plus y squared less than or equal to 4. So that's a set of points inside the circle x squared plus y squared equals 4. And we're considering the top half of that. So that's a circle centered at the origin of radius 2. And we're just looking at the top half, and it's everything inside of there. Okay, so we can't describe the entire boundary in one equation. Half the boundary is going to be the circular part, half the boundary is going to be the piece of the x-axis. So we'll say the top guy, what did I call it? 1 or 2. We'll say the bottom guy is piece 1 of the boundary. And the top guy is going to be piece 2. Okay, so step 1, we'll call this whole thing our region D. Let's find the critical points in D, and let's check the value of our function at any critical points in D. Okay, so we set the partials equal to 0. So our function of our partial of G with respect to X is going to be 2x plus 2, set it equal to 0. Partial G with respect to Y is going to be 2y minus 2, set it equal to 0. Lo and behold, oh, I believe I might have made a mistake on the exam. But yeah, okay, or on the solution. So the first equation tells us x is equal to -1, and the second tells us y is equal to 1. For some reason I thought I got 2, 2 there. Let me see. Wow. Jesus Christ, guys. No, that's always embarrassing. Okay, so we get the point negative 1, 1. That's another place I gotta fix. So we get the critical point negative 1, 1. We need to make sure that this is inside the region of consideration. Otherwise, we don't care about it. We only care about points inside D. So is the point negative 1, 1 inside the disk x squared plus y squared less than or equal to 4, y is greater than or equal to 0? Well, y is greater than or equal to 0. And when you plug in the point 1, 1, negative 1, 1 into the first inequality, you get x squared plus y squared is equal to 2, which is indeed less than or equal to 4. So since it's in there, we're going to check our equation at that point. So we get 1 plus 1 minus 2 minus 2. So we get 2 minus 2 is 0, minus 2 is negative 2. And we will come back to that later. Just going to add that to our list, come back to it later. Okay, was that the main point of confusion, Caitlin? Or would you like me to go on? Okay, yeah. Note to self. Honestly, I thought I would be get through all of these quicker than I did. And around the midpoint, the wine started kicking in, and that just made the process even slower. So that certainly did not help. So my apologies. But this is good. We're figuring out where the problems were. Okay. I didn't write down the interpretations for number 2. That's kind of a weird one because you don't have a lot of great this one is not an easy one to put into words, but let's look at it. Let me just share the screen here. I was not a fan of that piece of this. Okay, so we have an equation describing the pressure of a fluid moving through a pipe in terms of the radius and the speed of the fluid. So we need to calculate the partial with respect to r at 3, 2. And okay, so what did I calculate the partial with respect to? Two to be 9/8. Okay, so that basically means so the partial with respect to r Okay, so in words, P sub r is the rate of change of the pressure with respect to radius r at at v equals 3, r equals 2. So in other words, that's not really a sentence describing what it does. So it means, so you're at, the radius is equal to 2, the velocity is equal to 3. So suppose you keep the velocity the same. And suppose magically, what's the meters per second? So suppose you keep the velocity constant of your fluid, and suppose magically you can change the radius of the pipe. So if you increase the radius to, or you change the, let me say, change the radius by a little bit, to say r plus delta r, then the pressure is going to change by 9/8 times delta r, basically. Wait, did I get 9/8 or negative 9/8? Nope, that's right. Okay. And so that's kind of in words what the rate of change is telling you. If you change r by a little bit, by delta r, sorry, not r plus delta r, we were at 2. So instead of being 2, it goes to 2 plus some little change, delta r. The pressure is going to change by approximately 9/8 times that delta r. So that's sort of how we would interpret the derivative, the partial.
So essentially the 9/8 is the rate of change of pressure as radius is also changing?
Yes,
Okay.
right. Yeah.
Thank you.
Exactly. P sub RV is even stranger. But yeah, so yeah, so like in the solutions, so I can hang on, I could also post the solution he wrote, but he didn't give one for that. Yeah, that one's even weirder. So it's the rate of change. Okay, so okay, yeah. So we have the rate of change there is going to depend on R and V also. So if we look at the rate of change with respect to R, now with respect to V, and so on and so forth, it's a little weird. It becomes less like intuitive what it actually means. So I don't think that's a great question. But the first bit is sort of it's good to understand what the partial with respect to R means. That's how I usually think about it. But yeah. Anything else you wanted me to say about number 2? Okay, so quick question about number 10. What is that, Marissa?
For the partial with respect to x, I got 3x squared minus 3y squared, but you just put 3x squared.
Once again, my goodness. Yep. Cool. Yep, so let's do number 10. Wow. Bloody shambles. Add it to the list of shame. Okay, so number 10. Let me do this one real quick just so I can get the answer. So s of xy is x cubed minus 3xy squared x is root 3 plus t squared, and y is, oh, nope, 4 minus natural log t. So we want df dt when t is equal to 1. Yes. Okay. Oops. Not a partial, because it's just a function of t. So df dt, of course, is we do our tree. We see it's the partial of f with respect to x times derivative of x with respect to t plus partial of f with respect to y times the derivative of y with respect to t. So the partial of f with respect to x should be 3x squared minus 3y squared. Partial of f with respect to t is going to be t over square root 3 plus t squared. Partial of f with respect to y is negative 6xy. Why you do this? And the partial y with respect to t is going to be negative 1 over 2. Okay, so we know we can plug in t equals 1 on that, but we also have x and y showing up. And if you're evaluating a derivative at a point, then you need a number. You should not get any variables anywhere in there. So we need to know what x is at time 1 and y is at time 1. So x at time 1, we get square root 3 plus 1 squared, we get 2. And y at time 1, we get 4 minus natural log 1, which is 4. And when we plug those in, we get 12 minus 3 times 16. So or we get, yeah, 4 minus 16, negative 12. So negative 36 times 1 over 2. Negative 36 times a half, plus negative 48 times negative 1. So we get negative 18 plus 48, we get 30. 4 minus 1, is it 4t?
Yeah, it's 4t minus.
Oh, I missed that. Sorry. Y is 4t. Yes, you're right. Okay. And so then this should be 4 plus 1. Wait. That was wrong either way. Okay. So we get 4 minus negative 1 is 5. Okay, so we get negative 18 minus 240. So we get negative 258. Should be right. Okay. Okay. All right. So we got a lot of stuff. So let me go down the list. Okay, so number 18. All right, I will go back and fix that one. Number 18, if you solved for y and z in terms of x, would you get a different answer? You should not, but let's see. So 18, f of x, y, z is 2x plus 4y minus 4z. We want to find the max and min on the sphere. X squared plus y squared plus z squared equals 9. Okay, so we got a Lagrange problem. Okay, so this is going to be our g of x, y, z. Also, I had forgotten to assign 14.7 and 14.8. I'm making those due. So 14.7 homework is going to be due on Friday. If you'd like some practice and you have time before the exam and you're done with all these, you can go ahead and do those. But if not, I would prioritize the exam problems. But the 14.7 is going to be due on Friday. 14.8 is going to be due on Saturday. Okay. Okay, so 18. So the partial of f with respect to x is 2. And lambda times g sub x is going to be lambda times 2x. The partial of f with respect to y is going to be 4. Lambda times g sub y is going to be lambda times 2y. And the partial of f with respect to z is going to be negative 4. Lambda times the partial of g with respect to z is going to be lambda times 2z. And then we also have x squared plus y squared plus z squared equals 9, which is our constraint equation. So we have to find lambda, x, y, and z satisfying these equations. So clearly, lambda equals 0 is not possible. That's easy to establish right away. Because the equations become 2 equals 0, 4 equals 0, negative 4 equals 0, which clearly none of those can be satisfied for any x, y, and z. So we're assuming lambda is non-zero. Oops. Okay. So what we can do is you can get x, y, and z by themselves. I don't think this is exactly what I did, but this is something that should work. So we get x by itself. We get x is 2 over lambda. Y is going to be, no, sorry, 1 over lambda. X is 1 over lambda. Y is 2 over lambda. And z is going to be negative 2 over lambda. From this, let's write x and y in terms of z. Right. So what I did was I did x and y in terms of z and got x is equal to 2y, right? Because 1 over lambda is 2 times, or 2 over lambda is 2 times 1 over lambda. So x is 2y. And we also get that y is equal to negative z. Oh, sorry, x is equal to 2 times z, negative 2z. And y is equal to negative z. So I can replace x with something in terms of z and y with something in terms of z in the constraint equation and solve for z. You could do that, or if you like, you could solve them in terms of y. We see that x is equal to 2 times y, and z is equal to negative y. So then you can go to the constraint equation, replace x with 2y, and z with negative y, and then solve for y there. Or you'll still get the same answer. You'll get the y value, and then you go back to these relationships to get the x and z values. Or you could solve for y and z in terms of x. So if we do that, we see, oh my God, sorry guys. I'm getting old or something. I don't freaking know. Jesus Christ. Okay, sorry. X is negative 1/2 z. Good God. Okay. And then y is negative z. X should be 1/2 y. And z should be negative y. And then, okay, so if you solve for y and z in terms of x, we should get y is 2x, and then z is negative 2x. Okay. Sincere apologies, guys. This is unfortunate. Okay, so let's do what you had suggested. Probably the simplest thing. Taylor, solve for y and z in terms of x, and then plug them in. So we do that, we get x squared plus y is 2x, so 4x squared, plus negative 2x quantity squared, 4x squared, equals 9. So x is going to be plus or minus 3. And y is going to be 2 times that. Well, let's put in the points. So we get x is equal to 3, y is equal to 6, z is equal to negative 2 times 3, which is negative 6. And then we also get negative 3, negative 6, 6. And so plugging those in to our function, we get 6 plus 24, which is 30, plus 24, which is 54. And then we should get negative of that here, negative 54. So this is our max, and this is our min. Yep. So yeah, you should get the correct answer, Taylor. If you did what you did, probably. Okay, so for number 19, let's see what I possibly did wrong on number 19. Okay, so that one, I want to say I wrote something down about that one. That one's easy to explain, Ryan. Okay, I didn't explicitly write something down, but let me explain that now. So number 19, okay. Wait, the answer key says negative 162. For number 19, Ryan? Oh, that was for number 10? Oh, okay. Gotcha. Okay, I was like, ooh, Lord, I hope it's not for number 19. Okay, number 19. So the reason why, okay, so z is equal to 4 minus x squared minus y squared. And we're just considering z positive. And so this is just, you don't really need to draw this. But it's basically an elliptic paraboloid opening downwards. And we're not considering the entire thing. We're only considering the piece of it where which lies above the xy plane, where z is positive. So the boundary piece you're talking about is just this little bit down here, where z is equal to 0. And it's really easy to explain why we don't use that bit. And that is because whoops, xyz is going to be equal to 0 everywhere on there. Well, yeah. So we should make a point of that because it could be something. Could be something. Depending on the problem, that could be a thing you need to be mindful of. Yeah, it's going to be 0 on that whole piece. You should explicitly write that down. That's a valid point. It would be a good idea to write that down. Yes. Yeah. Okay. Okay, so sort of. No, here's actually why you don't need to do that. Here's actually why you don't need to do that. So when we got to the end, okay, so we got a few points when we did the Lagrange multipliers thing, and all of those were done not even thinking about the z greater than or equal to 0. So we got the let me share this screen. This is why I didn't. Okay, so we checked for lambda equals 0, and we saw it is possible to get some points for lambda equals 0. We saw points of the form 0, 0, z could satisfy that, and then plugging that in the constraint, we get z is plus or minus 4, or just 4. At that point, we get 0. We get the points plus or minus 2, 0, 0, where it's also 0. And we get the points 0 plus or minus 2, 0, where it's also 0. So we got those guys. And then when we assumed lambda is non-zero, we got some other points, 1, 1, 2, 1, negative 1, 2, negative 1, negative 1, 2, and negative 1, 1, 2. For all of those, our z is already positive. But even if, so the whole z greater than or equal to 0 thing, oh, hang on. Right. Let me make sure I didn't do something stupid here. No, there should be. Hold, wait. Right. Okay, so bro, please, thank you. If we just kept going, x, y, z should be unbounded. And so what are these things that we're finding in this case? So we do need to Yeah, so the z greater than or equal to 0 is needed. So let's make sure. I'm trying to think what this means mathematically here. So yeah, we still have xyz as lambda 2x squared, xyz is lambda 2y squared, xyz is lambda z. Okay. Yeah. Right, so we get x squared plus y squared plus 2y squared is 4, right? So y is plus or minus 1. Yeah, okay. Trying to think about what those points represent. Okay. Yeah, it is the z greater than or equal to 0 is needed here. Yeah, so I would mention on the set of points where z is equal to 0, x, y, z is equal to 0, and just keep track of that and come back to that later. Yes. Trying to think about what these points represent considering the whole thing. So there's 0 on there, 0 up there. Yeah, yeah. Sorry. I don't know if that clarified anything there, but I will actually need to think about that one for a sec. I don't see anywhere where I went wrong, but yeah. I'll have to think about what these guys represent. But yeah, sorry. Any other questions? Oh, so number 20 is clearly wrong, wrongly worded. So number 20, yeah. So it asks for it says, so the post office will not ship a cylindrical container if the sum of the circumference of the base plus the height exceeds 6 pi. That's only for a cylindrical container. That's the only info we have. So clearly the answer is supposed to be maximize the volume of the cylindrical container, the largest cylindrical container you can ship. That's a typo in the question, very clearly. And in the solutions, in the answers posted by the course coordinator, his agree with mine. Yeah, it's a typo in the question. Yeah, I was thinking about that too, but I was like, no, it's clearly they just mean it's supposed to be a cylinder. Yeah. All right, well, so if that's it, I will go ahead and fix the offending problems and upload the correct solutions. And yeah, I will be holding office hours tonight at 5:30. And I will make a Zoom lecture for that. And yeah, have a good one, guys. And good luck on your exam.